right, we are live and we are recording as well. So let's get started. Welcome everybody and Happy New Year, first of all. And Farm Beat is a topic we want to share today. And we have some special guests from Italy that have a significant experience in the field, pun intended. Now, my name is Stefano Tempesta. I'm a CTO at Connecting Software, Microsoft Regional Director and MVP, based in Australia. So long way, happy to be here. And today with me also have Alessandro Graspa, CEO at Julab, closer to you guys, based in Switzerland. Alessandro, welcome.
Thank you. Happy New Year, and you're welcome, everybody.
Perfect. So today's session is something that I don't even try to say myself. I leave it to our speakers. We have controlled environment farming. It's something quite innovative around hydroponics, aquaponics growing. What is it? How that works and how does it apply to our farms and even more than farming in general? Today, we have the pleasure of having three speakers, Federica Stella Blasi from University of Salento and Marco Mita from University of Salento as well, and engineer Lucio Colizzi. Smart Education Lab, as you can see on screen, but I leave them to introduce themselves and enjoy the rest of the session. As usual, the format, put your questions in the chat. We'll be able to read during the event. Keep them for the end when you can unmute and yourself and ask questions directly to our speakers. So, Federica, Marco, Lucio, I'll leave it to you to introduce yourself and start with today's session. So I stop sharing my screen and then I will give yourself the presenter. 1 second that I allow multiple participants to share the screen. Here we go. You can go now.
Okay, can I share my screen?
Yes, you should be able to do that now.
Okay, perfect.
Excellent. Yeah, we can see that.
You can see it?
Yes.
Okay, so hi everybody. Shall I leave my mask if you take yours? Problem. Okay, keep yours, please. Okay. Hi, everybody. First of all, thank you, Alessandro. Thank you, Stefano, for inviting us and for giving us the opportunity to showcase our contribution to innovation in the agri-food industry. It's a great pleasure for us. My name is Federica Stella Blasi, as you already heard, and I am the coordinator of the University of Salento's Urban Farming Lab, which is in Puglia, Italy. Italy is here, in Lecce, to be more precise. Our laboratory was funded in fall 2019, and our permanent staff includes 2 full professors, 2 associates, 2 researchers, and 6 research fellows. Of course, we are inside the University of Salento and in particular inside the Department of Innovation Engineering. Our mission and vision, I don't know whether you can see our screen. Okay. Good. Is increasing food production system sustainability and compatibility with the urban environment in particular. And our ambition is to ensure the food self-sufficiency, what people call now food sovereignty, especially of large urban centers, while respecting the environment. Okay, which are our main R&D activities? You know, our researchers, who are engineers and economists, like I am, and biologists, also ecologists, work alongside other research centers, as you can see on the left, but also SMEs, because we do industrial research, to design scalable systems that intensively produce quality food, serving big cities in particular. And we also work, our research also collaborate in the creation of new supply chains for the recovery of production waste, food waste especially, inspired by the principles of the circular economy. Then our main R&D results are smart food production system, and we're going to see two of them. Okay, our research areas of interest, and so the people who do the research are CE farming, especially the optimization of food production processes and also food waste processing. Integrating especially key technologies, enabling technologies from Industry 4.0. But the other research areas are food science, which includes especially improving the quality of food, but also biotech and systems ecology. Because as you can see, inside the urban farming laboratory, there are both researchers from the Department of Innovation Engineering, but also from the Department of Biological and Environmental Sciences and Technology. So, today we're going to discover two of our projects. I just showed you four. But today we're going to know more about the project ISEPA, Improving Sustainability, Efficiency and Profitability of Large-Scale Aquaponics, whose main topic is improving the competitiveness and the profitability together with the sustainability of urban commercial aquaponics. But we will also know more about the project SIMPLE, which is about indoor automated cultivation. And before leaving the floor to my colleagues, first of all, Marco and then Lucio, I just want to add some more elements about the first project, ISEPA. And I want to show you a video which summarizes the innovations that we developed within the project. Okay, I hope you could watch the video. Could
Yes,
you?
it worked okay. Yeah, it worked okay.
Okay. But before leaving the floor to my colleague Marco, who will explain better than I could the environmental monitoring system we've developed under the project ISEPA, I would like to know whether you or Alessandro know what aquaponics is. Do you know what's aquaponics?
Yes, I do.
What about you, Stefano?
That's the first time I hear. I'm a man of IT. That's
Yeah, but
something new to me.
I know because I'm working with you about some project on this topic, and I know for that, but I am not an expert.
Okay, let's try to explain it in short, because I don't know whether all the people that are connected now know exactly what aquaponics is. It's a production system, of course, a food production system, which combines the fish farming, especially within a recirculating aquaculture system, with soil-less cultivation of crops, namely hydroponics. So if you put fish farming and soil-less cultivation of crops together, then you have aquaponics, and that's aquaponics. Our interest is in large-scale aquaponics, industrial aquaponics, and all the work, the research work we did was to increase its sustainability and profitability, because there's a lot to do, especially if we want to let's say exploit its potential. So Marco, up to you. I'm gonna wear my mask again so you can take off yours, and so please, the floor is to you.
Hello everyone, I'm Marco Mita. I'm an engineer involved in the design steps of the monitoring system for the aquaponics plant that you can see so in the previous video. I'll try to explain shortly what we did in the lab. So we can let me say, we applied the philosophy basically of the industry 4.0 to this type of production. So we kept all the sensors, the actuators, the things that we can use to manage the recirculation water, the irrigation, the plant, the vegetable irrigation, and so on. And we make it smart. So we develop basically I can say custom electronic board to interface with this probe, such as the dissolved oxygen probe or a nitrogen probe or ammonium probe, to begin smart and to transmit the data, the collected data, to a central computer, where we can post-processing this data and support us to the decision to adopt on the management of this plant. So basically we achieved to have a monitoring system for the water quality, the real-time actuation of the actuator involved in the management of the plant, the real-time check of the filtration and the healthy of the self plant. it's the plant itself. Okay. So the designing steps is divided in four layers, because the structure of our monitoring system is divided in four principal layers. The perception layer that contains all the sensors deployed on the plant, the actuation layer, which is one of the low-level layer that contain all the actuators deployed into the plant, the transmission layer that basically was where the MCU, the microcontroller that managed the probe, manage the probe from one side and transmit the data to the central computer. And the upper level is a decision layer that is DSS, decision support system, hosted in a server where user can connect and download the data, see the trading part of the different parameter, the principal parameter inside the plant. This is basically the technology involved in the low level, so in the perception level of the plant. So the MCU, the low level core that interface with the probe or the actuator. We are talking about a processor from the expressive low budget microcontroller, 32-bit RISC microprocessor with 32 kilobytes instruction RAM, how you can read in the slide. And this type of microcontroller is think to for the IoT world, because he natively have a Wi-Fi board, a Wi-Fi manager that can allow you to connect directly on the net, on the internet, but it have also the physical pin that can permit that can allow you to manage physical things, so like sensors or actuator. In particular, in this type of application, we can find some pH probes, some redox probe that are digital probe, because they have a digital transmission of the data on a bus, on I2C bus, and some analog probe like the ammonium probe or nitrate probe. So we have designed a custom electronic board to interface these two different kind of communication protocol with our MCU. At the same time, we have to design also other custom board to interface with the actuators that need some power supply, or power electronic block, because for example, the water pump needs the AC power supply for his energy, for the power supply. Next, we can talk about the collector, the data collector, that is this Siemens IoT 2040, that is a single board processor and like Arduino board in the same SOC. This is a Unix based system with a Yocto distro, that is a Unix distro that manage all the peripheral on the board, and we use that to talk with other board on the plant. So to talk with our sensors and our actuators, and towards the upper layer with the server, with the web application, with other user interface and diagnostic interface. So we can see in the slide we have this main board with Interquark 32-bit processor with Yocto distro, however, so later. Some USB, some PCI socket, and on that we have a lot of application that we use to manage our sensors. So we have some Node-RED application that are the core of the application inside this board. With this language, we have all the power, all the how can I see with Node-RED in we can manage the sensor, because we implement all the protocol that we need. So basically we need to send some MQTT package to our sensor to activate and to collect the data that they collect from the physical layer, and we use some inside Node-RED application. We use some C++ firmware to manage low side the sensors transmission of the data, and we use also Node-RED to transmit this kind of data once collected in the main board to Telegram with the telephone application, the mobile application, for to control the plant directly from our mobiles. This is an example of the user interface that we can find on the server, the web application, where the web server. We can check the real-time parameters of the plant. We can set the rules that our plant have to follow. We can set the alarm to send in some case, maybe if some parameters exceed some thresholds. We can read the historical data of the plant and set the the web and technical parameters. So thank you.
Okay, here I am. I don't know whether they could. Okay, here I am. So as you could see, this monitoring system allowed us to control the plant, because when you have to deal with living animals, especially fish, you have to monitor the parameters, the fundamental parameters in real time in order to intervene if, as Marco said, there are some the values exceeds the threshold that we had already set. So before leaving the floor to our colleague Lucio Polizzi, I was wondering whether someone of you has questions, or if you want to leave the questions for the end, at the end of the meeting, tell me, Stefano, Alessandro, what we can do. Otherwise, I leave the floor to Lucio, who's not also an informatic engineer, is the president of a community garden, an extraordinary cook, and is the author of an interesting book on precision agriculture that he will present in the next few minutes.
So there are no questions in the chat at the moment. Okay. I suggest to go ahead.
Okay, let's go ahead with Lucio and the project Simple, which is about automated indoor cultivation. And Lucio is a project manager, so he can tell you more about the project, about the innovation we are designing.
Just a moment, I would like to share my slides. Just did you see the slides
with the project?
Did you see?
No, Lucio, we still see the contact us slide from Federica before. Federica, maybe you have to stop sharing.
Could you stop, Federica?
Okay, now that's better. I can see your slide, Lucio. Thank you.
Okay, perfect. Okay. Thank you, Federica, for your nice presentation. My presentation, I'm talking about the Simple project. Just a moment, I want to remove because okay, now it's perfect. Okay. Okay, the challenge of this project, the name is Simple. It's not so simple to work on this project, but Simple is just the name. The challenge of this project is to design and develop low-cost IoT systems for organic greenhouse farming. So we work in the field of biological agriculture, as we say in Italian. First of all, I would like to start with a definition. Typically, definitions you find on web for precision farmings are always complicated. This is my definition: doing the right things at the right time, in the right place for the right motivation. It's very simple. Precision agriculture was created to overcome some sustainability limitations of conventional agriculture. One of the most important is shown here in this slide. The typical approach for growing crops is to distribute agronomic input without considering variation within the soil. This means always assume that the soil is an ecosystem with homogeneous layers and characteristics. This is a wrong assumption. This is not true. This is the standard process, like a process template for precision farming. It's very simplified, but it's effective for understanding. In the first phase, in the stage number 1, are made the measurements. If I don't measure, I can't build knowledge about the ground. Unfortunately, each measure are typically point type. So is referred to a single point, and but it's necessary to be referred to an area. To do this, different approaches are used for doing this extension by means of geostatistic field. In the step number 3, area information together with the context information like weather forecasting, historical data, chemical information are matched together for defining what we call homogeneous zone. So an homogeneous zone is therefore a specific area of land that has the same needs in terms of agronomic inputs, such as water, fertilizer, or some mechanical task, tilling, so on. Going further in the process, knowledge about zone together with the crop growing model are used to build the so-called the prescription map. So this means answering to the previous 4 questions: what, when, where, and why to do something. Well, now at this stage, we have crops that rise on the ground, and thanks to the prescription map, a farmer can act something, or an automatic system can do acting for him. At the same time, other measurements are made during cultivation. For instance, on plant, it's possible to use proximal sensing instruments for getting information and improve the prescription. As you see, the feedback on the feedback in the stage 8 in the template process. Well, this is in this slide you can see an example of an integrated system for measurements. I worked on this machine some years ago when I worked in one of the bigger private research center in Italy with my research group. In the back side there is a penetrometer. In the front there is a georadar, a magnetometer. On the left and the right, camera for proximal sensing, and all the measures made by all these instruments are referred to a single point by means of differential GPS. In the bottom left, there is a picture of the calculated homogeneous zone by means of geostatistical approach. Well, fascinating, but expensive. As I say, precision farming is not a new concept. Research has been working on this method since 1980s, when GPS was released for civil application. Nowadays, in my opinion, producers have so far been able to afford such solutions. In many cases, complex precision farming systems able to, as I say, split the atom are very precious, but precised, but are much expensive. So have remaining nothing more than academic exercise. As we will see, I think nowadays there is a technological revolution. So I think it's possible now to overcome this barrier. I want to complicate the situation furthermore. In recent years, there has been a growing awareness about organic crops, about biological agriculture. We know that managing monoculture is simple, but has a low rate of biodiversity. Meanwhile, multi-cropping practices ensure high level of biodiversity. So this means high self-resilience of the system, of the cropping system. But unfortunately, organic farm cannot scale up because multi-cropping increase the management complexity. Typically has to solve some complex combinatorial problem to afford such kind of farming practices. This is the real revolution today. IoT allows to move from precision farming to smart farming. I don't want to go into details about what is an IoT device. I simply say that there are networked devices that can process something or give services to other devices or ask for services. In simple project, we deal about the opportunity that comes from open source and low-cost world. Also, when these kind of devices are joined with artificial intelligence approach. In this case, when we are talking about smart farming, smart agriculture. The template process could be this one. It's very simple. At the configuration level, the upper side of the slide, and for instance, an artificial intelligence system can solve the combinatorial problem of multicropping, or we can use also a mathematical approach to do this. So we can imagine an optimization process that uses as an input the economic strategy, economic challenges, and the intercropping criteria for defining the best cultural layout in output. In the management phase, in the lower part of the slide, the management phase means during the agronomical cycle, the system adapts its decision in real time because it has data that comes from the ground in real time or real world. Okay, this is some example of devices. I don't want to go in details. You already know, I think, what is Arduino and all the shield of this low-cost technology. I draw your attention to the device on the bottom right. The name is Node MCU. In my opinion, it will be a major player in the near future. It's not bigger than half a finger, but it also contains a Wi-Fi module embedded directly on it. So, well, we deal about this kind of systems in the project, in a simple project. We are indoor, and it's a very critical issue to acquire all the possible knowledge about the crop and the soil inside. The idea is to follow two alternative paths, two mainstream of research. The first one is to embed the upper part of what we call domotic. The first one is to embed a nervous system in a greenhouse made by the IoT devices, both sensor and actuators, and are controlled by a back-end decision support system. The alternatives do not use sensors embedded on the ground. In this case, the idea is to build a low-cost robot that perform measure transmitting the data to the back-end side for decision about acting or not. This is just for learning, just for smile. This is one of the solutions we are considering. It's a serious. We are considering for the low-cost robot to start with the inner part, the insider part of a kickboxing sack, adding a base robot, control the base robot by the shield Arduino, and build something other parts, other sub-assembly by means of 3D printing, and obtaining this kind of very low cost robots. Here, the insider part of the kickboxing sack could be similar to a tank, so we can fill it by means of water or fertilizer, or both water with fertilizer for fertilization. And it's possible to use it instead of to have sensors embedded on the ground. This is some details about the physical. I'm sorry, there are some words in Italian. Elettrovalvola meaning solenoid, electric valve, so a solenoid in English. As you can see, this is the physical architecture of the domotic approach. As you can see, we choose to use Node MCU for controlling both sensor and actuators. So this could be the farm of the future. Small, but smart. When necessary, it can scale up and handle the resulting complexity. But first of all, it's a farm, I think, self-resilience and sustainable. If you want to learn more, there are many sources online. Of course, I also recommend this book, which I'm one of the authors. Here, you will find this, I think, the state of the art in this application domain, a lot of experience, and in some cases also a lot of practical advices on how to build, to design and to build a system for smart agriculture. Okay, thank you. This is my last slide. If you have a question, I'm here. Thank you, Federica.
Thank you, Lucio.
Thanks, Lucio. Yes, indeed, very interesting. All right, it's time for questions. Anybody wants to type their question in the chat? I'm happy to read it. Or please unmute yourself and feel free to ask directly to our speakers. And I do have a question, although I'm not, as said before, ever use aquaponic or hydroponic in my conversation before. I've learned something new today, so thanks for that. Very interesting. My question is, how can you apply, such technology, or what is the experience that you guys have in apply these, this mechanism for growing food at scale? When I need a scale, I mean, say that you want to produce in this way food for millions and millions of people. Can this technology scale? Can this be applied to large population, or in some way, the production is too expensive or too difficult that it doesn't really work when you are looking at this sort of a large population? What's your experience in that?
Lucio, do you want to answer first? You have to unmute. Okay.
Can you hear me?
Yes.
Yes.
Okay. I can reply from the perspective of biological farming. Okay. You know that I'm both theory and practice about farming in biological or organic methodology. In my opinion, it's possible to produce a big quantity of food, of natural food, but it's an agricultural method that is knowledge intensive. this knowledge was well known from ancient human, and now we forget some practices, and we have to remember, for us, for next generation, this kind of practice is a very high knowledge intensive. If you have this knowledge, you are able to produce more food, big quantity of food in a natural way. Okay.
And by the way,
technology could be a great instrument for managing this quantity of knowledge you have to manage. Okay, to take decisions. For instance, we are working on the first layout configuration. If you want to have if you want to use, for instance, synergy between spaces that are traced in some well-known metrics that are on literature. If you use this synergy for have a little area of your garden where you are growing food, it's very simple. But if you want to scale up and you want to produce in hectares of land, the combinatorial problem is impossible for a human to solve. So technology could solve this kind of problematics, this kind of issues.
Interesting.
Stefano.
And yes, sorry, Federica, go ahead.
Yeah, I would like to add something more.
Please.
The last slide, or I don't know, I don't remember if it was the last slide by Lucio, said that future farms are small and smart. You can feed a lot of people, and you can think of doing it. For example, designing a network of farms. Our next project, this is what we are working on, for example, is building as I said, smaller farms which serve local communities. So you can have the same result for this case. So you can feed a lot of people, but you'll do it with small farms, which are obviously easier to manage.
So we heard the story from the engineering perspective from Lucio, so technically feasible, but is it also sustainable financially? So you are a person of economy, Federica, from what I understood.
Yeah. Well, this is a challenge. This is a challenge, and that's why commercial aquaponics has failed over the years. I mean, in modern times. Because as you know, as you understand, commercial aquaponics means high investment costs, but also high operational costs. This means delivering high, really costly products on the market, food products. And well, it depends on where you are. If you are in California, you'd buy tomatoes priced, I don't know, $10 per kilo. But if you do it in Italy, well, it's almost impossible. So economic sustainability is one of the biggest challenge of commercial aquaponics, and that's why you can't find, well, this is one of the reasons why you can't find commercial aquaponics everywhere in the world.
Yeah, very good point. Okay, my last question, if you don't mind. Later challenge. I follow your blog, Stasera mi porto a cena fuori. I take myself out for dinner tonight. And you always show some great places and try different food and wine and so on. How does it taste, this food? Is it comparable to the normal one? Does it taste good?
Okay, second challenge. You know, I am a food passionate. This is my greatest passion, and also Lucia's passion as well. And yes, I've got a blog. I do love telling stories about my food experiences. And I'm a sommelier, so I really love enjoying great wines. I do love food that taste. The taste is good, of course, and you know. I tasted some hydroponics tomatoes, aquaponics tomatoes, and honestly, their taste was not that good. Still, we can work on it. That's why I told you it's the second biggest challenge, flavor. Flavor is an important thing because food is not just about nutrition, it's also about flavor. And research must do a lot of work in this sense, at least if we want to have, if we want to produce good, let's say good food, quality food from hydroponics, from aquaponics.
All right, so it's good for feeding people, but probably not to take your date out for dinner. All right, very good.
I'm doing it by myself.
Exactly. Federica, do you have the possibility to read the chat? We have two questions. One from Paul.
Yes.
He's asking, what is your opinion about measuring carbon content? Yes.
Okay, Lucio, I think that first, you can answer the first. What is your opinion about measuring soil carbon content in multi-cropping agriculture?
I know that the low expensive approach for measuring carbon is to use infrared. At the moment, I don't know if there are sensors, low-cost sensors for doing this. At the moment, in our project, we do not measure the carbon, and we measure the electrical conducibility or the moisture temperature, the moisture of at the different layers, different deep. But not carbon. Paul Bright, one important thing in this moment, I think infrared is not so accurate. I want to talk about this. When we use for instance, a sensor for moisture born for Arduino Shield, we are talking about a sensor that it costs about $2, okay? $2. Of course, the precision is not an accurate sensor. This kind of sensor are not so accurate like that one used in professional or applications. But if we want to arrive in a farm and not in a laboratory, in academy, in a university, we have to lose some things in accuracy, precision, and choose devices that are not expensive. This is due to the sustainability of the system that we are developing. So sure, infrared approach is not accurate, but the question is, we need such accuracy. We really need such accuracy for growing vegetable.
Lucio, so that was my question. The reason I ask is there is now a market in carbon credits, so farmers can make some money by this means. So it could be important for farmers.
what could be important? The precision of the device that may take measures.
The carbon content. The farmer can earn money from the carbon content.
For marketing purposes, you mean?
No, I mean the market in carbon credits. So the more the carbon in the soil, the farmer, at least in the US now, the farmer can sell carbon credits.
Okay.
But in multiple cropping approach, the carbon typically is under control. Is under control. Is under control by means of the methodology that the farmer use for growing vegetable.
Yeah, maybe I wasn't clear, but by putting more carbon in the soil, the farmer can earn money by sequestering carbon into the soil.
Yeah.
That's why he needs more accuracy, you said. That's why you need more accuracy. Because you can demonstrate that you are storing carbon,
Precisely, yeah. Right now, there is no good method to accurately and low cost measure the amount of carbon. And therefore, for the smaller farmers, they cannot get the full value of the carbon going into the soil.
I see. So,
Lucio,
do you want to ask something more about Paul's question?
Oh no. We are not in our simple project. We are not take measure about carbon in the soil. So if we for these issues and we will find some solutions, some economic sustainable solutions, I will share.
Thank you, Paul.
Thank you, Paul.
There is another question, maybe for you, Marco.
Yes.
Do you want to see in the chat? They're asking how to manage the data collection process from a technology perspective.
Yeah, sure. Basically, our sensors read our ESP, the microcontroller, read the values of the sensor revealed from the sensor from the I²C from analog sensor, and encapsulate it in a JSON structure with other information needed for the upper application, and transmit by MQTT towards a MQTT broker that hosted on the Siemens IoT 2040, where are processing basically are processing. We are organized by the node in the Node-RED application, and then towards transmit towards the DB, so the web server that save it in a DB and organize it for a graphic user interface to manage this kind of information from by a human user.
Biologists, for example, or the operators which deal with the fish farming and also the soil, the hydroponics cultivation.
Or the users that have to manage the plant, technically the plant itself. Our idea is to follow up this kind of management of the data with some artificial intelligence application. So this will be the future steps, the future designing step.
Maybe let me specify shortly here. So and thanks for explaining the workflow here. So my question focused a little bit more on the scalability of the approach. I would say for the test setup, for the demoing, I think it's a pretty good approach. It's a lot of hands-on setting up the IoT sensors together. But if you want to scale, if you're thinking about like a couple of hundred farms are providing sensor data and more having in mind to share this data within or between different farms, I think you need a strong back end and a proper structure, not for visualization for one farm, for one user, but also pushing for a more collaborative way to making use of different sensor data through sharing, validating, cross-validating the data as well, and then have let's say larger benefits out of that.
Yep, but right now we deal with the management of the single plant, so we focus.
So it's more about the individual measurement to get some knowledge on the measuring itself than scaling that in a broader sense.
Yep.
Yes, that's a test bed. That's why
we want, in this first step, we want to focus on the single stage problematic issues. So we want to solve all the problematic inside the plant. So to manage safely the itself plant. Then once we solve this kind of management problem, we go towards the synergy farmers management.
Thank you.
All right, so in the interest of time and respect for everybody's time, we can stay here and talk for hours and hours, and maybe we'll do it another time on a dinner on hydroponic food, but it needs to improve the quality, please. Then how about we say thank you to our speakers. I'm sure there are a few other questions that we can follow up also offline. I will publish this video recording. If Federica, Marco, Lucio, you want to share the slide deck or a version of it, I'm happy also to socialize with the community. Thanks a lot so much. I learned personally a lot today. And any last word from anybody before we close?
I'm sorry, there is a question that comes from Johannes Lauer. How are managing the data and the data processing, collecting, storage, and processing from a technological point of view, and how does it scale for applications? In simple project, we use just a backend server developed in PHP, is a server application, and for the data storage we are using a simple relational database. Okay, for scaling up, I think for the dimension of greenhouse that we are, so the number of sensors that are inside indoors, it's enough to use a relational database. I think for scaling in terms of number of sensors, number of actuators, and the timestamp when you take data from the ground, for instance, you can scale with a no-relational database. A graph database could be the better solution in this case.
Okay, thank you.
All right, beautiful. Thanks, everybody. Have a great day, and we'll see you soon next time. The next event is on February 18, and we'll be talking about robotic automation and remote controlling. So completely different topics. We go from the farm to the factory. So follow us on the Meetup for more news and obviously for an update on this event itself. Thanks again. Enjoy the rest of your
Thank
day.
you very much.
Thank you.
Thank you.
Bye-bye.
Bye.
Bye-bye.
Stay healthy. Bye-bye.